So today's lecture on conditional expectation. This is a very important concept. This is usually mainly used for inference theory and in statistics. So what is conditional expectation? We know what is conditional density or conditional PMF. We define like that: f of x given y, say y equal to y. Sometimes writes y equal to y of x, and some author write in this form also: x y given y, x given y, and x given y. Right? But the first one is better notation in the sense that it is actually a function of single variable, because y is fixed here. This small y is fixed. Remember, this y is fixed. So this is like a function of this form. So this is like a function x. This is the whole thing is the function. So this is the basically the function from real to real. So that's why you have to take only one input x. So this is whole thing is a function. This whole is a function. Function. We write f for function. This is the, we can write g for function. This is the whole notation. This is the function. This f x given y equal to y. This whole thing is the function. Is a notation for the function. Why you are writing this form? You are just actually were telling that it's for a given small y equal to y. What, and we are going to the conditional distribution of x when this y equal to y is given. And we know this function is actually this function is actually this is a right, just a division of this y equal to y is just f of x y by f of y equal to y. Sometimes in this previous lecture we write this as f2. So these are joint distribution, joint density or joint PDA, joint PMF given with the marginal. That's the marginal at the point y. So now we should not write x that. We should write is a dot here. So I'll take that input here. We write the input here. Sometimes we write a function like that, some function from R to R, or say D to R. We write something like that. And so that means this is actually that f x y is fixed divided by that marginal. That marginal may be sum, maybe integration, according to this discrete or continuous case. Now we know this. All of you know this. Now, what is the expectation? What is the conditional expectation thing? So this is the definition of the conditional expectation. So it's like a random variable. For a fixed y, this is a random variable. For another y, this is another random variable. And we can talk about the conditional part. So x and y are two random variables defined on say the probability space omega script a for script s, the probability measure p, and let h be a Borel measurable function. Always that any function should be a Borel measurable function and be a Borel measurable function. Borel measurable function. It's a Borel measurable function always. We always take a Borel measurable function and assume that it is provided, or assume that expectation of hx is defined, exists. This is exists and finite. Exist means infinite. Then the conditional expectation, we define the conditional expectation. Conditional expectation like that, conditional expectation of hx given that y equal to y, given some value of y equal to y, given y is written as, sometimes we write as this as written as expected value of hx given y, but this is the x. So we are taking the expectation of what the x, the random variable x, But this that y, the random variable y, we're not taking the expectation on that. Basically, it's for some value of y. So y equal to y. So this is a random variable. So this is a random variable basically. So after taking the expectation, this is again a random variable. It's not a real number because that y, capital Y, we are not taking any expectation on that. We're not taking the summation about that y. So for some y equal to y, or say y equal to y1, this some expectation is this. Y equal to y2, another expectation. So there's several list of expectations. So list of numbers for different y. And this for different y, that there are different probabilities, and these numbers have the different probabilities. That means it's a random variable. So this is a random variable. Remember, this is a random variable. Is a random variable. So remember, this is a random variable. This expected conditional expectation is a random variable. Is a random variable. And take and this random variable hx given y takes the value. What where takes the value? That takes the value hx given y equal to y, that small is fixed. Obviously, the y is in the spectrum of y, capital Y, the small y, given and defined by and this with the probability, this probability of y equal to y. This takes the values, this with probability y equal to y. And what is the value? What is the value of this? What is the meaning of this expectation of hx given x y? So the meaning is this: the expectation of hx given y. This meaning is this. This has for discrete type. We just write it for discrete type, and similarly you can write for the continuous type. So this is discrete type. This is sum over all x. So it is only sum over the x, not over the y. Probability hx, probability of x equal to x, given y equal to y. So this is a conditional probability. If x and y are discrete type, and obviously this probability of y equal to y must be positive. Otherwise, this provided this. Otherwise, this expectation doesn't define. If y equal to y, probability of y equal to y, small y is for 0, then this conditional probability is not defined. So this conditional expectation is also not defined. And for it is for the discrete case and discrete case. And similarly for the continuous case, this is not a summation. It is just a integration minus infinity to infinity hx and this conditional density y equal to y x, or you can write x given y dx for the continuous case. So these are the some definition for the expected value of the conditional expectation. Remember, so this is a random variable that takes values, and this obviously this the probability of this is so this is random variable. So this random variable, remember this is a random variable. So this is a random variable. Remember, this is a random variable, and this random variable takes value y with probability. Sorry, no, not taking value y. Sorry. Not taking value y. It is taking the values of that thing. That taking the values this one. The conditional expectation of x given y. This thing, that what is we define this. This is the remember, this is a real number. This for discrete case we define like that the summation, and this continuous case we define. So right hand side is the so just a minute. So this is the left hand side is a random variable. Remember, this the left hand side is a random variable, and right hand side is a real number. Now, what is the definition of the right hand side? You already defined for discrete constant. That probability of taking that random variable is this value is just the same as the probability of y taking the value of y. for the discrete case. For discrete case. It is for the discrete case. So, and for this continuous case, what is this? Then the density function of this conditional expectation at the point that expectation of hx given small y is the density function at the point y of y. So PDF of, and for continuous case, the PDF of that random is a, remember, that is a random variable. This is the random variable. This expectation is again a random variable. Is at that point, at that, this, remember, this is a real number. When we write the small y is just the PDF of that y at the point y. So this is the basic idea. Similarly, we can define expectation of some hx, hy given x is a random variable. So it is defined. Obviously, provided this must be exist, otherwise this is a problem. This must exist. Provided that is exist, provided this expectation exists. Expectation hy is exist. This is important. Otherwise, this is it's not defined. Now, some result is this. Some important result on this conditional expectation is this. The expectation of the results are the first one. The expectation of the constant random variable c. C is the constant random variable. Given another random variable y is just a c. Next is the expectation of ax plus by, x and y are two random variables given, or say this x plus b is better, x plus b, given that random variable y, conditional expectation of this is nothing but a into conditional expectation of x given y plus b. This proofs are easy and AVR constant. It's left as a homework and you can easily find in the any book. Now, more generally, if G1, G2 are two Borel measurable functions, always you have to take the Borel measurable function. Remember, Borel measurable functions. And if this expectation of G1, remember this to define something, this expression must exist. Expectation of G2x is exist. If we assume that these two exist, then what happens? Then the expectation of A1 G1 x plus A2 into G2 x given some y is nothing but, this is just nothing but A1 into, and you can extend for it n somewhat all this AI GIX. Is AI the expectation of some over expectation of say GI here G1 x given y plus A2 the expectation of so G2 x given y. These are very trivial to prove. It's a very trivial result. And the fourth one is also important. The fourth result is very important. The fourth result is this. If this random variable is positive, that means the probability of taking positive get a non-negative value is 1. Then this conditional expectation x given y is a positive random variable. Remember, this is a random variable. Expectation of x given y is a random variable. It's not a real number. It's a random variable. It takes some values with some probability. And the last one again is just a generalization of this. The fourth one you can show from the fourth one is that if x1 is greater than or equal to x2, two random variable, that means the probability of x1 greater than or equal to x2 is 1. Then this conditional random variable x1 given y is bigger than with probability 1 bigger than. So some random variable bigger than some random variable means it is with probability 1. Or it is means just with x given x is greater than equal to y means the probability of x is greater than equal to y is equal to 1. So similarly, we can define the moments, conditional moments. We just define the conditional expectation, so we can define the conditional variance. Similar way, we can conditional variance of x given y. So it is nothing but the similarly define. You can define the variance. So variance of x given y. This is again, this is a random variable. Remember that probability of the variance of x given y is a random variable. So this is, we can easily define this is like that: expectation of x minus expectation of x, that whole square. This is a variance thing given y. So this is a random variable. The right hand side is so here the function is actually that Borel-Merzel function is x minus expectation of x whole square. So this is the function. So similarly, we can define the other raw moments and this moments and this central moment, everything. So this is a basic definition. Now, so and this theorems is very important. Two theorems are very important. Theorem number 1 is this. The two important theorem is this. Let expectation of hx exist. We have to take this, otherwise the other conditional expectation is not defined. Then expectation of, you just take the expectation of hx given y. Then again, this is a random variable. This is a random variable. Now this random variable on y, all the values where what y is taking value, that random variable takes also take the same value. If you again take the expectation, now just expectation on y, then this is equal to just expectation of hx. This is very, very important result. So what is the proof? I'll show it, proof it for discrete type, and the conditional, the continuous is the same thing, same proof, the similar, left as an exercise. So what is this? So say x on a discrete type. Discrete type. One more problem is this: if say x is discrete and y is continuous, or y is discrete, x is continuous, there is some problem. Then it will be integration, summation, mix up. But we are just in our syllabus we are taking x, y as both are discrete or both are continuous. So if one is discrete and one is continuous, then this is slightly tough. Now, what is expectation of this? Expectation of hx given y, and then that expectation. So this is expectation of what the y is. So what is this? Remember, this is somewhere all y, and this random variable takes the value. What? This takes the value. This random variable takes the value. We know this with that probability. That takes the value expectation of hx given y, and with that probability y equal to y, because this random variable takes this value with probability y equal to y. Now, what is the definition? What is the expectation of this? So this takes the value. So no need of writing that. So we have to take just the value only. Sorry, we have to take the write down the only value. No need of writing this expectation that random variable. So it is just a sum word. What is the definition of, by the way, what is the definition of some expectation? What is the definition? So definition of some expectation is like that. Say expectation of say y. What is this? This sum word all y, and then some probability of y equal to y, and that y value. Similarly here, so forget about this. This we are taking expectation on that, this expectation. So sum over y into probability of y equal to y, and that y, Now, what is y here? Because y, the capital Y is taking value of small y, but this is a random variable. Remember, the random variable is not the y. We're not taking the expectation of y. We're taking the expectation of this random variable. Say this is a z. Now we have to find when capital Y equal to small y, then what is the value of this random variable? The value of this random variable is just this, given small y. And by definition, what is this? By definition, this expectation is expectation of over yx. And this is just hx, and the conditional probability x equal to x given y equal to y, and one more probability of y equal to y is there. Now it is almost done, because what is this? This is nothing but what is the probability of x given y, x equal to x given y equal to y into probability of y. It is just, we know this is hx into this is just probability of x equal to x. This is the conditional probability, definition of conditional probability. Oh, sorry. This is the just the margin. Sorry, the joint. This is just joint. So we know what is the conditional. The conditional is joined by this marginal. So this conditional into marginal is the joint. Now this is the precise definition of. We know this is precisely the definition of expectation of hx. This is a precise definition of hx. Expectation of hx. This is the definition of h equal to hx. So similar proof for this for the continuous case. We just replace. We have to replace this all these things in summation by this integration, improper integral. Now, next theorem is very interesting and very important in this inference theory. If this expectation of x square exists, that is finite, that means variance also exists. If the second moment exists, that the expectation of x exists, and then variance also exists. In that case, the variance of x, just like expectation of x is expectation of x given y, and then taking the expectation. Now, this is, you have to take the expectation of x given y. You have to take the expectation of x given y. So just one corollary must be, we must mention the corollary of this. The previous thing is like that. If hx equal to x, then what is this? Then the expectation of x given y. If you are taking first expectation, conditional expectation, then the expectation on y, that is expectation of x. Now, for this one, if you're taking the expectation of x given y, and then you are taking just variance of that. Now, this is not the variance. Conditional expectation, then taking variance is not the variance. Variance of the variance is not the variance. The variance of x given y, and then taking again the variance what of y is not the y. This is basically the variance part, and another part is there. What is this? This is a variance of x given y, and then taking the expectation. So this proof is very important, and this theorem is very, very important because it actually gives the idea of the ANOVA, like analysis of variance. So if x is there and some x, there is a joint x and y, two random variables. This is basically the marginal variance is nothing but the sum of two different variants. What is this two different variants? The first variance is the conditional expectation. So it is like for a fixed y. So it is a intra-block variation, so inter-class variation. So first part is the inter-class variance for a given y equal to y. So for a given y equal to y, you are taking the variance. You are taking the average of this and taking the variance. So it is sort of inter-class. Sorry, it is inter-class. So basically, you are taking the variance of on the y. First part, the variance on the y. So you are taking the fixed y, and they're taking the average of all these things, and then take the variance of that. And second part, what is the second part? Second part, basically, you are taking the, for a fixed y, you are taking the variance. So it is intra-block, between the block. The second part is the between the block. Fixed y, you are taking the variance, then taking the average of this, all this variance. And the first part is the inter, or the within the block. So you are taking the average on a fixed block and then taking the variance of that. So this is basically the nothing but the ANOVA. What ANOVA do? This is a basic theorem. So what is the proof? The proof is, the theorem is, most important theorem is this. And so we are going to the proof. Proof is not tough. It is not complicated. It is quite easy. But interesting is this. The proof of this is just that. So we are taking, what is the variance? What is the left hand side? What is the right hand side? Right hand side, you know the variance. And what is the variance? Variance is the expectation of that some square. Expectation of some, if you say it is Z, then the expectation of x conditional on y, the whole square, minus, you know, what is this? This is the expectation of x given y, and again expectation and then square. You know this. This is the definition of the variance. Variance of z equal to expectation of z square minus expectation of z whole square. And again, this part is, what is this? This is the expectation of what? This is the expectation of the, again, the variance of this. So what is the variance of this? This is the expectation of x squared given y minus expectation of x given y, and then whole square. So this is the, what is the next part, next line? So it is expectation of expectation x given y, then whole square. And this part, we know, this is already proved, this is nothing but the expectation of x, and then whole square. Now what is this? What is the other part? Now this is the expectation of x square given y, and then again taken as expectation. So this is just expectation of x square. And what is this part? This part is a minus expectation of x given y whole square. Now it is clear. This towards same part. So it is cancel out. So what do you left out? We're left with just expectation of x square minus expectation of whole square, which is just the variance of x. So right hand side is just the variance. So what is the corollary? Then corollary is this: if expectation of x square is finite or exists, then what happens? Then the variance of x, that the variance is greater than the expectation of the variance of this conditional variance, because this part variance, this part is actually positive. Variance part is always positive. You know the variance part is always positive. So that's why this this variance of x is greater than or equal to this thing. And is the equality hold? Yes, equality hold. Equality hold. When this equality hold, can this equality hold? Then equality hold. So equality hold. Equality holds if and only if this part, that variance part is 0. So variance of expectation of x, conditional expectation is 0. So when this conditional expectation is variance is 0, some random variable is 0 means the random variable itself 0. The random variable taking 0 probability, 0 with the probability 1. That means the random variable x given y, the expectation of x given y, this is a random variable. That probability is 0, taking value 0 is the probability 1. So what is this? This is equivalent to say that this probability of that expectation of x given y taking value 0 is the whole probability 1. Now when this some conditional expectation is 0, that means this is the only function of x. Expectation of the, if it is a function of x, if this conditional thing is function of x, x is a function of y. Basically, x is a function of y. So that is x is a function of y. So if x is a function of y, then this once y is given fixed, then x is also fixed. So then this expectation is, then it will be 0. So this expectation is part is 0. So sorry, it is not a 0, it is a constant, right? Oh. It may not be 0. The variance 0 means it is a constant. Sorry. Constant for some c. Sorry. The variance 0 means the random variable may not be 0. The variance 0 means the random variable is constant random variable. When this expectation is the random variable is constant, that means the x is totally defined by y. So once the capital Y value is given, then this x also fixed. So that x is a function of y. And the last thing is this. For independent, what happens if it is independent? So the last thing is this. The last result is this. If x and y are independent, then what happens? Then this conditional density is actually the marginal density in that case. And obviously, if expectation of hx exists, if this exists, then what happens? Then expectation of that hx given y is nothing but expectation of hx, and similarly expectation of hy. H is a Borel measurable function. Then this is the expectation of hy. This if these are independent. So that means this thing is just a trivial thing when this is this x, y are independent. So this is for today's lecture. Any question? Any question on that? নেক্সট দিন আমরা শুরু করব হচ্ছে লিমিট থিওরেম। আচ্ছা, আমাদের কি অফলাইন ক্লাস শুরু হয়ে যাবে?
এখনো বলেনি, তবে শুরু হওয়ার কথা আছে বুধবার থেকে মনে হয়।
তাহলে দেখা যাবে বুধবার থেকে আমরা অফলাইন ক্লাস শুরু করব। ওকে,
ঠিক আছে,
নেক্সট দিন আমরা লিমিট থিওরেম শুরু করব।
ঠিক আছে।